Hello and welcome to today's NCT Data Science Seminar, and this is in cooperation with Heidelberg AI as well. The seminar will be recorded to make everyone of you aware of this. And yeah, it's my pleasure to welcome all of you here in person and online, wherever you are, with this camera. And also, it's in particular a pleasure to welcome Jakob Zech here as our speaker today. We actually know each other from the ZEISS model-based AI project, which is quite interesting because I think you come more from the theoretical and foundational side, whereas we more, come from the applied side. And the whole field of operator learning, which will be the topic today, is more or less the connection there. And I think we can learn quite a lot from each other. A bit to Jakob's background, he's coming from mathematics, studied in Vienna and Zurich, did his PhD at ETH in Zurich as well, and went afterwards to MIT for a postdoc. And we are happy to have him here at Heidelberg University and the IWR as a junior professor since 2020. And yeah, happy to have him as a speaker today. Thanks for coming.
Thank you very much. So thank you very much for the introduction and also for inviting me. So what I'm going to talk about today is neural operator surrogates, and the results that I will present are mainly based on two papers. So one of them is still work in progress, but they're with the following co-authors. So Lucas Herrmann, he's now in industry, Carlo Marcati is at the University of Pavia, and Christoph Schwab at ETH Zurich. And I want to get started with explaining the problem that we ultimately try to solve here. And so what we want to do is we want to approximate some kind of operator that I denote by this calligraphic G throughout. And this is assumed to be a mapping that goes between two spaces, X and Y. So these will in general be infinite dimensional spaces, something like a function space. And what the G does is it takes an A in the input space X and it maps it to a U in the output space Y. So this is the notation that I adhere throughout. And the situation that we will have in mind is that the input relates to the output through some partial differential equation. So through some kind of physics. So this is what we see, for instance, in the top row, where the input A, it's the diffusion coefficient of the second order elliptic PDE. This is the standard example that people consider. And U is the output of the operator. It's just the solution of the PDE. And so therefore, A is a function on this little square. U is a function on this little square. What this particular model describes is a so-called groundwater flow. In this case, the input is something like the permeability of the ground. So it's like a material property. And the output U is like the pressure head of a fluid. So this is an important situation where A will correspond to a coefficient of the PDE or forcing term or boundary condition and so on. Another important situation is that where A, this is what we see in the second example in the second row, does not describe a coefficient necessarily of the PDE, but it describes the underlying domain on which the PDE is posed. And so what I mean by that is, here, what the input is like the shape of this little obstacle, and the output is the flow of a fluid around this obstacle in the channel. And so the fluid, I can describe it with two things, the velocity field U. So here in the Navier-Stokes equations, this will be the U, and P is the pressure. And so I plug in, what I plug in is the shape of the thing, and what comes out of the operator is the velocity field and the pressure. And so again, I can think of the A simply as a function describing, for example, the boundary, and therefore it lives in some function space again. Okay, so these are two examples, and of course we can come up with many other relevant examples here. But the important thing to keep in mind is that the input, it always describes somehow the problem configuration. The output is the system's response. So mathematically speaking, the solution to the PDE. And this is what we would like to approximate. So to make this more rigorous, I will assume in the following that G is a mapping between two separable Hilbert spaces. So throughout, X and Y will be separable Hilbert spaces, so something like a Sobolev space, HS, or something like this, which is the natural space in which to define these PDEs. Our goal is then to compute this surrogate of G, and in particular, we want to compute a cheap surrogate of that, right? And so the motivation behind that is in many problems that we solve in modern applied math, or also in machine learning, we are in a situation where we have to compute some kind of statistics, or we do some kind of optimization on the output. And that means whatever algorithm you use, you're going to have to use a lot of evaluations of this forward map, or of its gradient if you do some kind of optimization. And this is just going to be very, very expensive, because every such solve requires you to solve a PDE. And basically, you just want to speed up this process, and therefore you want to have a cheap surrogate. So another application would be something like real-time evaluation. So imagine you have some kind of control problem. So you simulate kind of the next step, and you want to react very quickly, like adjust some kind of control variable very quickly, and you don't have the time to run a PDE solver, right? And so if you have some cheap way of evaluating that, you can get around this problem. Optimal experimental design would be an example which is based on optimization. And then a very big and important class of these type of problems are inverse problems. So where the situation is, I'm given information on the output U, I'm trying to recover what was the input A. So something like Bayesian inference. And again, a lot of different methods and algorithms exist which can solve something like this. They're based either on optimization, like computing a map point. So what you would have to do is you would have to maximize like a posterior density. In this case, the posterior is a distribution on the input space X, or they're based on sampling. And in both situations, if you use something like MCMC, you have a lot of sequential evaluations of G. And so we would like to tackle this problem now using neural networks and using something like supervised learning. So meaning what I have is data pairs AI and G of AI. And based on this, I want to learn the G. So I want to learn the physics in some sense. And so why or what are possible reasons for using this kind of approach? So one possible reason is the one that we see here, which is written in red. And it states that in order to learn G using supervised learning, in principle, I don't necessarily need to understand the physics behind the thing. All I need is like measurements. So in practice, when we have some kind of model, it's almost always a simplification, right? So there's certain physical phenomena or effects which you don't take into account to make the thing simpler, or you don't even understand. But if you learn based on data, you also don't necessarily need to. Although that said, it's always better if you do understand the physics behind your problem, because this gives you more information. Okay, the second reason, which for me is the more compelling one of why to use neural networks, is that the problem I'm trying to solve here, so approximating this map G between those two Hilbert spaces, is a high dimensional or even infinite dimensional approximation problem, because these are infinite dimensional spaces. And now by very classical theory, so approximation theory, but also statistical learning theory, we know that if you have no further information on G, let's say G, all we know about G is that it's Lipschitz continuous, you're going to suffer from the curse of dimension. And you have like hard mathematical statements which basically tell you in this kind of situation, there is no algorithm which can approximate this thing at a reasonable cost. Now in practice, of course, we already use algorithms, for example, based on neural networks, which can approximate this operator G. And so the reason is, so why is it then possible if we have mathematical statements telling us it's not possible? So the reason is that in practice, we always have some additional structure in G that we may not be aware of, but that exists. And by that, I mean some kind of intrinsic low dimensionality in the problem, right? And the hope is, or this is something that we have learned in the past couple of years, both theoretically, but also in practice, that neural networks are fairly good at detecting such intrinsic low dimensionality. So what I mean by that is, for example, a situation where you have what people refer to as small n widths, which simply means that, so G goes between those infinite dimensional spaces, but maybe the input which I'm interested in lies in a low dimensional subspace. So this is what we mean by small n widths, or it could lie on a low dimensional manifold. Then you would have some kind of non-linear low dimensionality, or it could be that this G can actually be well approximated by a composition of low-dimensional functions. So there's very different notions of what this low dimensionality could be, but it turns out that neural networks are fairly good at detecting such things from data. All right, so this was just the motivation. And now what do we want to do? So if we want to theoretically analyze this thing, then these are some of the questions that you would like to answer. So the first one is, using neural networks, can we even approximate such G? So this is what is referred to as universal approximation in the neural network literature. And if these were finite dimensional spaces, this is a very classical statement. You can always find a network. If that approximates your mapping to the desired accuracy, if you have a big enough network. So this is universal approximation. Now, in the infinite dimensional case, it's not completely trivial, but it turns out it's also not so hard to prove something like this if you use the right architecture. Now, what already gives us, so this is more of a sanity check in the sense that it's a statement of the type, as I mentioned, given a big enough network, you can get to arbitrary accuracy. But if this big enough network must be so huge that in practice we can't really use it, it's still not a practical algorithm. So the next question is, so what is actually the cost, for example, in terms of the number of parameters in the network that I need to use? What is a suitable width? What is a suitable depth of the network that will give me some desired accuracy? And of course, then we can also ask for the cost in terms of the number of data points. So I also need data to train this whole thing, right? And then the question is, so how much data do I actually need to get a reasonably good approximation in this high-dimensional regression problem? And so this last question I'm going to address at the end, but not in the context of, let's say, statistical learning theory, but basically I will give an explicit construction, and this will give us some insight. If we do not have random data here, so I don't choose the AI randomly, but I choose them at very specific points, how many of those evaluations of G I need in order to get a good approximation. All right, so here's the overview of my talk. And so what I will start with is explaining a bit the architecture. Afterwards, I will essentially give our main results on these neural network circuits. And in the end, I will talk a little bit about the case of Gaussian random fields, which is a very popular method to discretize the input or to model the input, which is what engineers often use in practice. So let's start with the first one. And basically, I want to explain, so what is actually the algorithm that I'm using here? Here's again the problem. G is this mapping that takes A in X to G of A in Y. And I want to approximate this using a neural network. And we will keep it simple. So I'm just considering a multi-layer perceptron, so just a standard feed-forward neural network. And so since the input comes from this infinite dimensional space X, the output lives in this infinite dimensional space Y. And the network is, by definition, a mapping from some Rn to Rm. So it always goes between finite dimensional spaces. The first thing you have to do is, what we do is we adopt this standard encoder-decoder type of architecture where you start by, you take the input A and you apply some encoder, which simply is performs some kind of dimension reduction. It takes the element in X and it maps it to something finite dimensional in Rn. And the decoder does the opposite thing on the other side. It takes the output of the network, which is a vector in Rm, and maps it back to Y. Now, if you do this, then of course, in general, you're going to lose information here, right? Because I'm starting with something infinite dimensional, I'm mapping it to something finite dimensional. And in general, you will lose too much information there. So the question is, if we talk about something like universal approximation, why is it even possible to approximate my operator like this? And so to motivate this, let's think of the following situation. Let's say this is a function that is, for example, in L2. So it's an L2 function on the square, so square integrable. And what we do is we do simply map this function out to the first n Fourier coefficient. So I do a Fourier expansion, and I map it to the first n Fourier coefficient. So meaning I keep the low frequency part of the function, I chuck out the high frequency part of the function. So this essentially just becomes like a low pass filter. And this will give me a reasonably good approximation of the original function, or will allow me to reconstruct a good approximation of the original function if this A has only, if it's fairly smooth in the sense that the high frequency part is small, right? And so if I have that, then I can assume that I get a good approximation here, and same thing on the output side. So if we do that, then the question of universal approximation boils down to the question of, can I approximate a map from Rn to Rm here? And as I mentioned already, in finite dimensions, this is like very classical. And this is morally the argument how you would prove that given such an operator G, and using this kind of architecture, you can obtain universal approximation, meaning if you choose here a big enough network, also meaning that this N and M, of course, must be large enough, we can approximate such a map. Okay, let's make this a little bit more concrete now. So what do people choose as encoders and as decoders? So I want to recall two very popular frameworks. The first one is the Deep O-Net, first proposed by Lu Yin and Karniadakis. And essentially, they use this type. So this is now going to be the surrogate, the approximation of our operator. And so let me carefully walk you through this formula. So what happens here is the following. I get the input A, and then they say the encoding we simply do by evaluating this function at certain points in our domain. So if this is a functional input, for example, on this 4x4 grid. So I plug in the A, and what I end up with is, in this case, a vector in R⁴, so 4x4. Now, this encoded input, it then goes into the network. So I denote the outputs of the network here by Gj. And therefore, the outputs of the network depend on two things. The encoded input and theta are the network parameters. And finally, I need to map back to the output space. And the way they do this is by taking these outputs of the network as linear expansion coefficients with respect to some function system eta j. So eta j is just an element of y. So you, in a linear fashion, you just take a linear combination with respect to the network outputs here. And this function system of the eta j, they also learn during training. It's itself a neural network. And this is the Deep O-Net architecture. Another fairly popular one is the PCA-Net, first introduced by Hesthaven and Ubiali in 2018. And it is also based on a linear version of encoding and decoding, but the encoders and decoders are slightly different. So what they say is, well, in the end, I want to learn this operator based on these data pairs of input-output, aig of ai. So the first thing we do is we find the best n-dimensional subspace representing the input data. So I do a principal component analysis. On the input data, I find some orthonormal basis, which spans this best approximating n-dimensional subspace. And then the encoder simply computes the coefficients, so the inner products with respect to the spaces. Again, I send everything through the network, and then I decode in exactly the same way as the encoding. Namely, I first determine an m-dimensional space best representing the output data, and I expand in terms of this output basis. So again, it's a linear way of doing this decoding over here. Yeah, and this is the PCA-Net. So what I'm going to do is somewhat similar to this, but in some sense it's more general, because I will not just use orthonormal bases here, but I will use the concept of frames. So let me first recall what a frame is. So in the following, I will always use the notation psi j to denote a fixed frame on X, and psi j tilde will be its so-called canonical duoframe. What does that mean? So if psi j is a frame on X, then in particular, we have the following two properties. The first one says that any element A in X, I can represent it in terms of the frame. So I can write down an expansion, expanding in this frame. And the coefficients, or one possibility for the coefficients, are given as the inner products with the dual frames. And so assume that psi j is an orthonormal basis, then of course the dual frame would be the frame itself. So, and then I have equality here, which is just an expansion in orthonormal basis. And so in this sense, it's more general than orthonormal basis. The second property is a generalization of the Parseval's identity for orthonormal systems. So it says that for any such A, its norm is equivalent to the small L2 norm of the coefficient squared. And again, if this were an orthonormal basis, I would just have equality here. But for a frame, I get only equality up to some lower and upper multiplicative constants. So it's more general than an orthonormal basis, and this will play an important role later on. Now, using this, so with psi j being this frame on the input, eta j being this frame on the output space, what is now my encoder and decoder? It's very simple. The encoder takes an A and maps it to the first n frame coefficients in this expansion. So it takes the inner product with respect to the dual frame. And the decoder takes a finite sequence, C1 to Cm, and does a linear expansion in terms of the output frame. So I just use frames to represent inputs and outputs, is the message here. If I do this, then again, the key question here is how much information do I lose by doing this? Because this will tell me how good my approximation can be. And so in order to mathematically quantify this, we introduce now a new set of Hilbert spaces. And we do this as follows. So let Wi, so W stands for weight, be something like 1 over I. So think of 1 over I. It's a sequence that goes to 0. It's not L1, but it's almost L1. So it's L1 plus epsilon for any positive epsilon. And then I fix for the moment S larger than 0. And now I define XS as a subspace of X such that its norm squared is defined as the sum of the coefficients squared. But then I multiply with this weight, Wi to the negative 2s. So since the Wi goes to 0, the Wi to the negative 2s goes to infinity, and the s tells me how fast this thing goes to infinity. So if I increase s, I make this norm here stronger, and therefore these spaces here are nested. So x2 is a subset of x1, is a subset of x0. And what is x0? So if I plug in here s equal to 0, then I just end up with the L2 norm of the frame coefficients. And OK, this is exactly the x norm up to a constant, right? So therefore, x0 is just the same as x. And I do the same with yt. So for x and y, I introduce these scales of Hilbert spaces by introducing these new weighted norms defined in terms of the frame coefficients. Now let's do an example to make this a bit more clear. So assume I choose psi j simply as an orthonormal basis. So I told you an orthonormal basis is in particular a frame, and I choose now an orthonormal basis of the space, for example, L2 on the interval 0, 1. And the weight is now exactly just 1 over I. And with this definition of XS then just amounts to the Sobolev space HS with 0 boundary condition, okay? Because I only take the sine functions, but I would also take cosine functions. I will get here HS. But this is how we can think in the following of HS is a function space, and the S somehow tells us how smooth are those functions, because this is the space for which the first S, if S is integer, if the first S derivatives of the function are still L2 integrable. Okay, so if this was too technical, here is the takeaway from this slide. The important thing is I introduced this XS and YT, and the reason why I introduced this is because if an element belongs to one of these spaces, then basically the S and T tells me how fast its coefficients go to 0. And that's because I have that this norm is finite, right? And so because I know the increase of the weight, this tells me something about the decrease of the coefficient. So this is the important thing to keep in mind. Okay, so this concludes the first part. So what I told you now is I'm using this encoder decoder type of architecture with linear encoding and decoding, basically just representing my inputs and outputs using frames. And the reason why I do that is because it allows me to split or to partition somehow the inputs and the outputs in important parts corresponding to low frequencies and in less important parts corresponding to the high frequency part, because I assume the high frequency part is kind of small. And this is what will allow us to obtain some kind of approximation here. So with this, we come to the second part, where I want to talk now in that situation about our results on the network in the middle. So in this setting, what can we say about the network in the middle? And to explain that result, first, I need to introduce two assumptions. And so the first one is I said that G is a mapping that goes from X to Y, or from a subset of X to Y. And what I assume now is I assume some regularity of this G, namely I assume it is complex differentiable. So it is holomorphic, meaning that, so if X is a Hilbert space, then X plus IX is a complex Hilbert space. And I assume that it's a complex Fréchet differentiable map from this complex Hilbert space into the complex output space, right? So if you're not very familiar with this notion, it's not so important. Basically, I'm saying this is a very, very smooth map. In particular, it's C infinity. But to make this condition more precise nonetheless, what I do is I introduce a cube. This is why it's called C. R is something of a radius, and S corresponds to, or tells us how fast the coefficients go to 0 for elements in this cube, in quotes. Because I'm looking at, so R just scales the whole thing, and then I'm looking at an expansion in terms of my input frame, where the coefficients of the Yj belong to -1, 1. And then I scale everything with this weight, Wj to the S, which somehow goes to 0. So for larger S, it goes to 0 faster. And in this image, what you see now is this cube will correspond to this line. So one-dimensional cube is just this interval. And I assume that I have some open subset of the complexified space XC, such that G from this open subset in the complexified space to the complexified output space is complex differentiable. So a technical assumption, but importantly one that we can show for many PDE models, in particular the ones that I had on the first slide. So this is not like unreachable, let's say, or impossible to have. Now the second assumption, so the first one was this holomorphy, so strong smoothness of this map. And the second one is a boundedness assumption, namely I assume that G of A belongs to YT. Again, I assume that I have a certain decay on the coefficients in terms of my output frame. This is what this assumption says. And under these assumptions, we then have the following theorem. So it tells us that for any n in n, there exists a neural network Gn such that my operator surrogate consisting of the encoder composed with a network composed with a decoder approximates this forward map G uniformly on a ball of radius r in the space XS. And I obtain some kind of convergence, some algebraic convergence in terms of the number of network parameters. So the convergence rate here is the minimum of S-1 at t. The epsilon here is just a positive but arbitrarily small constant. So whenever I write epsilon, it's positive but arbitrarily small, meaning there will be a constant hidden in this less equal. And this constant depends on the epsilon, and it blows up as epsilon goes to 0. But essentially, the convergence rate that I obtain is this minimum of S-1 and t. And so again, what is S? So I'm taking here a ball in the space XS. So this will be my inputs, and therefore the S has to do with how fast do coefficients, frame coefficients in the input go to 0. And the t tells me how fast do frame coefficients in the output go to 0. And so what is the relevance of this thing here? So it tells you G, this mapping between two infinite dimensional spaces, I can approximate it with a convergence rate that is completely independent of the dimension, because the dimension of this problem is infinite. And I'm taking as input a ball in an infinite dimensional space. So this is why this is not at all trivial what's written here. Typically, what you would assume here is that you have like a very bad D dependence, and that this kind of problem is intractable. It turns out it is not if you have this kind of assumption. So let me give you an idea on how we prove that. And so basically the proof uses 3 key components. The first one is we exploit somehow this multi-level or multi-scale structure of where I have separated important from non-important parts in the input and output. So this is what I mean by multi-level. Then I'm using the very strong smoothness of this map. And finally, I'm using a connection between polynomials and neural networks. But I want to start with this multi-level thing. And so to explain that, let's first take a step back and recall what is the network actually supposed to do in an ideal case. And what I want the network to do is take the input coefficients, so the coefficients of A with respect to my input frame, and map it to the output coefficients, so the frame coefficients of G of A. So this is what I want to learn. Now, in practice, I can never learn this map exactly, the reason being that I truncate here. So from this information, I cannot reconstruct the A Therefore, I cannot reconstruct the G of A. So it's not possible to learn this, right? But in an ideal world, this is still the mapping that I want to get. Now let's take a closer look at those output coefficients. So I'm representing my output in terms of a frame, and so a frame, you can think of it, for instance, as some kind of wavelet basis. Yeah. So it splits somehow the function into these coarse features and finer features. Okay. And now I know something about my output. I know that the coarse features are much more important than the fine features because I have a decay in those coefficients. This was my assumption. So I assume, or this comes out of the assumptions of the theorem, that the coefficient corresponding to such a coarse scale feature is much, much bigger than a coefficient corresponding to such a fine scale feature. So if I want to approximate those coefficients in terms of the relative error, I better get this one right? Whereas this one, in terms of the relative error, really doesn't matter that much because it is so small. So the idea is now invest a lot of degrees of freedom in the approximation of the important feature and invest only very few degrees of freedom in the approximation of the not so important fine scale features. And this is, of course, just a sketch, but this is the idea of how we do the proof. So if I say I want to approximate this coarse scale feature on the output, I will reserve a big chunk of the network to approximate this very well. Whereas for a fine scale feature, I will only reserve a very small part of the neural network. In particular, a fine scale feature on the input might not even have to feed into this fine scale feature on the output because its influence is insignificant. It's so small that we don't even need to consider that, right? And so the proof, therefore, is based on very carefully analyzing, doing a sensitivity analysis, basically, of how does each of those outputs depend on each of those inputs. So that's the key thing in the proof. Let's do a concrete example now. So I'm considering operator G that maps A to U, and this is basically the same example that I had on my first slide. So I'm mapping this diffusion coefficient, or I'm taking here the exponential of the diffusion coefficient, but it doesn't make a difference, to the solution U, and I'm doing this on some domain omega, and think of, we have zero boundary condition here, for example. Now, what do I choose as an encoder? So for the encoder, I'm just going to do basically a Fourier expansion on this square in 2 dimensions, and I assume that this square, so which is just 0, 1 squared, it contains my domain omega, which is some polygonal, convex polygonal domain in 2 dimensions. And so the thing is, so why am I doing this on the square? The thing is, on the square, I can very easily find an orthonormal basis that is stable with respect to the Sobolev spaces, right? And so then I represent a function A on this square, and then I truncate it to this omega, and then I want to map it to U. And therefore, I can use as an encoder just this Fourier expansion. Now, for the decoder is much more critical because the U, it just lives on this set omega. And now on omega, I cannot usually find an orthonormal basis that is stable with respect to the Sobolev spaces. And this is exactly the reason why we use frames, because it turns out that you can find so-called Rie spaces, which is in particular a frame, that is stable in Sobolev spaces. And again, why am I so keen on using these Sobolev spaces, or why do I want stability in Sobolev spaces? Because Sobolev spaces are the correct spaces to formulate such PDEs in. So this is where the solution of the PDE lies in. And essentially, these constructions are based on finite element constructions. Yeah. So what they do is they use, so this is what's done in this paper by Davidov and Stevenson from 2005, and there's others. They basically just use finite element constructions and then take different spaces between different discretization levels, so to speak. But my point is, this is something you can actually compute and work with in practice, whereas, as I said, an orthonormal basis I could not necessarily compute in this domain. And this is what the theorem in this context then reads. So there exists a neural network Gn. It has O of n network parameters. And I can approximate now G of A for all A in a ball of radius R in the Sobolev space HS with my operator surrogate. I measure the error in the H1 norm, and I obtain some kind of convergence rate. So the convergence is in terms of n, the number of network parameters, and the rate depends on S. And so what is S? S is the smoothness of the input. So I'm taking A in a ball in the Hilbert space HS, and I'm taking the supremum here. So in particular, if I plug in S equal to 5, then I get here convergence rate 1/2. And if you know something about finite elements, then you will know that this is the best convergence rate you can get for, in general, for a solution on such a convex domain, which will belong to H2. And for an H2 function, if I measure the error in H1, I can get convergence rate 1/2. So that means if the S is large enough, I can, with the same complexity as computing just one single PDE solution, I can approximate the whole operator on a ball. So for all of those different inputs in a whole ball, I get the same convergence rate as if I would just compute a single PDE solution. Okay, so that's quite interesting. And as I said already, this is just one example, of course, a simple example, but essentially this carries over to also more complicated PDEs. All right, so this concludes now so how much time do I have actually? Okay, so I will probably skip over the last part, but this concludes then this second part. And so just to summarize, what I did here is I explained what we can say about this network part in the middle, and we obtained these dimension-independent convergence rates because we assume this very high regularity and because we exploit this multi-level construction that we obtain through these frame decompositions of the in and output. So the last thing I just want to shortly talk about is the case of Gaussian random fields as input. And so the reason why this is interesting is because it's a very common model that people use in practice. But there's a key difference to what I told you so far, because so far I assumed that my input, it comes from a ball in a Sobolev space. And a Gaussian measure can take values basically on the whole space, right? So it's concentrated in a small area, but with small probability, it can also take very large values. So this is why these compactness-based arguments that we used here will not carry over. But let me make this a bit more precise. So I assume in the following that gamma S is a centered Gaussian measure on X. And so it's a Gaussian measure on this Hilbert space. So without going into too much details, a Gaussian measure on a Hilbert space, just as a Gaussian measure on Rn, is uniquely defined by two things, its mean and its covariance. And the covariance in this case is an operator, a bounded linear operator from X to X. In particular, it's a self-adjoint trace class operator. As such, it has eigenvalues lambda j and eigenfunctions psi j, corresponding eigenfunctions that are orthonormal. And the reason why I denote this Gaussian measure by gamma S is because S will tell me how fast the eigenvalues of the covariance go to 0. Namely, I make this assumption here. So the lambda j, I assume the eigenvalues, they belong to L1 over 2s plus 1. So in particular, if S gets larger, then that means the eigenvalues go to 0 plus. Now, with this orthonormal system, I choose now my encoder as the following map. So it goes from X to Rn, and it simply takes A to the coefficients with respect to this orthonormal system. And this I call a Cahunen-Loew encoder because there's a very close connection, obviously, to this, if you're familiar with this, with the Cahunen, so-called Cahunen-Loew expansion. Namely, if A is a draw from this Gaussian random field, you can expand it in terms of this orthonormal system. And it's very well known that the coefficients here, if scaled by 1 over the square root of the corresponding eigenvalue, are IID standard Gaussian. So so this is the coefficient, and I know that this here is N01. So if I take the lambda j to the other side, I see that the coefficient has mean 0 and variance lambda j. And since the lambda j's go to 0, this tells me that the coefficients become more and more concentrated around 0. And in this sense, the S, which tells me how fast the lambda j go to 0, still somehow tells me how fast the coefficients of the input decay, but now in a probabilistic sense, because since these are Gaussians with small probability, they can still be very high. But it's a similar condition as before. So let me skip over this slide and just come to my result. So the network architecture that I'm using here now is I'm still using frames to represent the output, and then I'm using this Cahoon and Löw type encoder that I just explained to you. And in this case, I want to approximate now G with my operator surrogate. And I cannot take a supremum here anymore because my input is a draw from this Gaussian measure gamma S. And so the natural metric to measure the error in is then this Bochner space, L2 X to Y, and X is equipped with the Gaussian measure gamma S. And so in this sense, I want to approximate this operator. And in order to prove a convergence rate, we again have two assumptions mimicking the assumptions that I had in the first part. The first one is that this G should be a holomorphic map. And now in this case, it should be holomorphic on this strip in the complexified Hilbert space. So on the x-axis, you see the real Hilbert space X. On the y-axis, you have I times X. And therefore, this whole thing here is the complexified Hilbert space. And what I assume is that this G from this strip of width to tau into the complexified output space is complex differentiable. Okay. And the second assumption is also similar as in the first part. It's a boundedness. I assume that G of A belongs to the space YT. So again, telling me that I have a certain decay, the output coefficients. And additionally, there's some growth condition, but that's not so important now. And then we have the following theorem. So if S and T are positive, then again, for any n, there exists a Rayleigh neural network Gn such that the error decays like n to the negative minimum of S comma T plus epsilon. So once more, the epsilon is just positive but arbitrarily small. And the convergence rate depends on two things, S and T. So T, as before, just telling me how fast do coefficients on the output decay in this sense. And S telling me how fast do the eigenvalues of this covariance of the Gaussian measure gamma S on X decay. And again, I just obtained this algebraic convergence rate where we do not observe the dimension anymore. So right, so since the time is up, let me just come to my conclusions. So what I talked about here is the following. So first, I explained our architecture, which was based on these linear encoders and decoders using frames. I then told you if we have a very high regularity G in the sense of complex differentiable, then we can obtain algebraic convergence rates in terms of the neural network in the middle. So it is possible to approximate these abstract mappings between Hilbert spaces even on a ball in the input mapping to the output. And finally, I talked a little bit about these Gaussian random fields. And the message here was you can again obtain dimension-independent convergence rates. And in this case, the convergence rate depends in particular on how fast the eigenvalues go to zero, which has to do with how concentrated is this Gaussian measure in the Hilbert space. If the eigenvalues are very small, then basically it's going to be very, very concentrated. And therefore, it's not so surprising that you get faster convergence. And the last part is what I skipped. So in principle, we can even give a deterministic construction of this based also not on random input, but on very meticulously chosen input points. And then we can obtain these convergence rates, which I gave you only in terms of the number of network parameters, also in terms of the number of data, namely the number of data points, so the number of forward evaluations that you need is just exactly the same n as the number of network parameters. So it's a convergence rate in everything, and it's completely deterministic and not just in probability. Right, so finally, these are my references. The highlighted ones are in particular the ones on which this talk is based. And with this, I end my talk, and thank you very much for your attention.
Yeah, thank you very much, Jakob. We've got some time for Q&A. I think, until 12. So I probably start with the first question. There are probably some online as well. Please type in your questions into the chat, then we can read them out here. And if you got a question here in the audience, feel free to just raise your arm. So my first question would be, in practice, when we want to do this, we obviously always have to go to some finite dimensional spaces. Basically, for us, it might be images as inputs and outputs. And what we usually have as a problem is that we have data that we learn on that has some specific discretization during training time, but we also want to learn the underlying physics. And then during inference time, maybe it is some completely different discretization. Do these frames that you introduced, do they cope with this problem that you have different discretization scales during training and inference?
To some extent, yeah, because it's like a hierarchical basis. I can always refine more, right? So in principle, you could also have, for example, training data at different scales. Let's say you have a lot of low resolution PDE solves, like, which is much cheaper, right? And you can use that. And then you have a couple of higher resolution PDE solves, so done on a finer mesh, in order to approximate the high frequency part to some extent. So I would say this comes like very natural with this kind of framework. And also people have started, so independent of us, people have started using frames for exactly these kind of tasks, because it turns out like it's fairly stable. In particular, it's more stable, it seems, than just evaluating your input functions at certain grids, because like the frame, like the frame coefficients are somehow smoothing it out, right? Because like you have to compute an inner product with respect to certain functions. And so therefore, it seems that this has some theoretically interesting properties, but based on some work that other people have done, also in practice, it seems to work fairly well. Yeah, but I think there's more work to be done here, and yeah, so to check how exactly one has to implement this. So in particular, to what I just mentioned in terms of using training data at different resolutions.
Sounds interesting. It might be a new method to use for us as well. Cool. Are there any questions in the room? Not? Are there any online? So let's have a look. Jens writes, fantastic talk and explanations. Thank you very much. How can you integrate physical constraints in your framework?
That's a good question. So, I mean, so far we don't.
I mean, you basically do by just taking the lower frequencies more, the lower dimensional components more into account, right?
Right.
Because physics by nature is not very high.
Right. So yeah, it depends on what we mean by physical constraint. So we do to the extent that you basically just explained, namely, I exploit properties of the operator that I know a priori. For example, I know a priori that my solution belongs to H2, and this will tell me how fast do the coefficients on the output decay, and this will tell me like what is the dimension I should choose on the output, right? And the same goes for the input. And so this we can, in principle, we can explicitly tell you. So this may be also important to mention. In order to prove these convergence rates, it's not, the network architecture really does depend on the operator, but it does depend on the operator in a way that we know. So we can give you that architecture, but it's not like a generic thing which will work for any. Then you will not end up with the optimal convergence rate. And so we do exploit properties of the operator to this extent, but I think often people are interested in adding something like symmetries or stuff like that. And so this we don't really do so far, but obviously that would be very interesting on how to do that, but yeah.
Cool. Is there another question online? Not yet. So is there a question in the room? Some asking faces. Oh yeah, there's one. Jan. Quickly get the micro to you.
So currently you presented like your neural network is usually just a normal multi-layer perceptron. Are there, like, can you comment on like what other possibilities you have there? I'm thinking of invertible neural networks that can be particularly useful when you then want to actually solve the inverse problem, or can you comment on this? What are opportunities in this field there?
Right. So in terms of the network architecture, so maybe let me start by I present everything for ReLU, and this is not really necessary. You can use other activation functions. You can prove similar things. So sorry, what was it that you just mentioned?
Invertible architectures that you can easily go back.
So I don't know if that makes much sense here, because assume, for example, that your operator G maps everything to a single point, and then this is just not going to be an invertible map that you try to learn, right? So so we have not tried or we have not thought about the case of using invertible neural networks, but I also think it depends a lot on what your operator G is, whether this actually makes sense. So if you, because you say, okay, I want to invert the thing, and in this kind of situation, it's going to be very, very unstable, right? So even if you can do that, I don't know if it's a good idea to do that. But another thing to mention is maybe that, so the result that I had was mainly in terms of the approximation theory, and this you can also extend to some other type of architectures, and you will end up with very, very similar convergence rates. So I stayed here in the framework of using a multi-layer perceptron, mainly for simplicity, but you could do other stuff for invertible neural networks. In particular, I haven't thought about it too much, I have to say. Yeah.
Thank you. All right. Thank you very much, Jakob. I think if there are no questions online, we wrap up the talk. And yeah, please give Jakob another warm round of applause. And thank you for your talk today.